Okay, so you guys had lots of practice on nomenclature on that worksheet. So I encourage you guys just to go ahead and go look at the key for all of those answers and check your answers. I'm not going to record a specific video going through every single one of those answers because it's a lot. So the next section we're going to talk about is reactions. So there's a variety of different kinds of reactions we've learned so far. So addition reactions is when you add something to an alkene. So we learned things like hydration, where you add water across an alkene, or hydrogenation, where you add hydrogen across an alkene, or hydrohalogenation, where you had a hydrogen and a halogen across the alkene. Those were all chapter 11 reactions. And then in chapter 12, we learned about oxidation. Which is the loss of hydrogen or the gaining of carbon-oxygen bonds. Gain of oxidation state is what that symbol means. Reduction, which is the opposite of oxidation, where you gain hydrogen across a carbonyl, for example, and you lose some of your carbon-oxygen bonds. We have hydration, which I just mentioned is an addition reaction, where you gain water across the bond, and then dehydration, where you lose water and create a double bond. We also have combustion. So you can have combustion of an alkane, or you can have combustion of a alcohol. Let's just write that in real quick. Okay, so the main thing to know for combustions is what the overall products are, or what the overall reaction is. So we need to have our heat in there as well. And then we have hydration of alkenes. Alkenes, which is one of our addition reactions. You have a hydrogen catalyst an acid catalyst is required for this reaction to occur. So pretty much all of the addition reactions require acid catalysts to happen. The reason for this is because they go through a carbocation intermediate, which we talked about a little bit as to why we get the selectivity of our products. So water is not an acid itself, so we need to add acid in order to get this reaction to work. And then remember that we also have our selectivity. So hydrogen ends up on the carbon that already has more hydrogen. So the rich get richer concept that we've talked about. Dehydration of alkanes, of alcohols, in order to make alkenes. So that's a typo right there. This is called an elimination reaction. You guys don't necessarily need to know that exact phrase, but a hydrogen catalyst and heat are required for this. So you notice that to go backwards, all you have to do from the alcohol to get back to the alkene is to heat up the reaction. So heat, whether you have heat in there or not, is really important when you're filling in your reagents. So dehydration is the opposite, as we've talked about. Reaction conditions can be controlled just based off of the heat. So there's the example there. Hydrohalogenation of alkenes. This is again an addition reaction. There's no catalyst required for this because our HX source is already an acid by definition. So like HCl, for example, hydrochloric acid. It has acid in the name, so you do not need to add an additional acid. And again, we add our hydrogen and our bromine across a double bond, and the hydrogen goes on the side with more hydrogens already. The rich get richer. Hydrogenation is a version of reduction. So we will call these hydrogenation, and these are called reductions. These all require some kind of catalyst, whether it be nickel, palladium, or platinum catalyst. My favorite's nickel, so just so you know. Alkenes and alkynes undergo a hydrogenation reaction with hydrogen and our catalyst in order to form alkanes. And then ketones and aldehydes will do reduction reactions to give the corresponding alcohol out of the reaction. Okay, and then oxidation is the opposite of our reduction. So primary alcohols, if in the presence of water, will go all the way to the acid, or the carboxylic acid, I'm sorry. But without water, it will stop at the aldehyde. Our secondary alcohols are going to do an oxidation to become ketones, and then tertiary alcohols cannot undergo oxidation because there are no hydrogens to be oxidized. No CH bonds next to that OH that can be oxidized. And then I think the last one, I might be wrong, is the oxidation of thiols to give disulfides, where you bind these two sulfurs make a sulfur-sulfur bond. So it's very different kind of oxidation than with oxygens or alcohols. So there's a lot of practice reactions here. Again, I'm not going to go through these particularly, but the answers will be online.